So first and foremost, we'll do a little introduction because we've got a new person on this episode with us tonight. So we'll start with you, my friend. Would you like to introduce yourself?
So, hi everyone, my name's David Powell. I'm joining Apprentice One-to-One today to just go through this scenario that you've been given or you're going to be given. Worked with Richard Harvey in my current role, worked with him previously, and been involved in the electrical industry since 1999.
A long old time then, mate. So you should know what you're doing by now. And everyone should be familiar who follows along with the podcast with Craig and Richard. And again, I think Richard's going to be driving this one tonight, so we'll let him take over shortly. But how are you first, Craig?
I'm good, thank you. I'm having a week off this week, so it's nice to just enjoy a bit of downtime and recharge the batteries, ready to go again next week.
Awesome. And you're having to suffer us for an evening, so that's ruining your holiday right away. Richard.
I'm doing a Scottish holiday, you stay at home.
Yeah. Richard, how are you, mate? I think you're going to lead us through the chat tonight on this example you put together.
Yeah, I mean, if I lead it and then the other expert panelists can interject as we go along. Me and Dave have managed to tag him along. I've enticed him today because I shared the little scenario with him, and we had a nice little engineers debate, didn't we, Dave, as we went through it? And Dave's got many years' experience. He's also taught the EAL level 4 design qualification, and similar to me, when I came through my apprenticeship, I did the C certificate, but Dave did the 2400, which has then obviously been replaced recently by 2396. So we got a C certificate, 1 2400 and 2 2396s with distinction. Is that right, Craig? Shaking his head. Yeah, you know, plenty of. And Dave's obviously been in the teaching space, similar to myself, for many years as well. So just saying, you know, if I could entice him in, it would add a bit of value, hopefully. So all good, yeah?
It should do. It should do. And we've shared this question already on the course of social media over the last week. For those of you who listened last week, you'll have heard us talking about it. It's been on the Apprentice One-to-One website. I've played around with it today and answered it using electrical OM to the best of my abilities, or I'm sure Craig will tell me I've made a mistake somewhere in there somewhere, because he's far more proficient at that than I am. I'm going to share my screen now, which includes the answers as we go through along it. Is that how we're approaching it, Richard?
Yeah, I think so. I think I've put the answers in the sheet that I produced last week, but similar to the other two scenarios that we did, I've kind of laid it out in such a way that it's easy to kind of follow, where you can use the various publications and get the relevant information from different tables, etc. So a little bit different this one to how I set it up last time. I had a bit less time, but with this one, you got a bit more homework to do. So there's a link directly to the manufacturer of the EV charger, so you might have to go and have a bit of a look there. And we've also decided that we're going to be using a new type of cable produced by Doncaster Cables, which I'm sure you've used, Mark. Very popular because it incorporates power and data, which may be a benefit to installing some of these chargers. So a bit similar to what we've seen before. Quite a bit of information. Got a nice little diagram.
Is my screen sharing just before you carry on, mate?
Yeah.
Is it?
Yeah, it is. Yeah.
Perfect. Carry on.
Yeah, and got a nice little drawing with a bit of information on there, and most of the stuff that we need should be more or less in the question. I haven't gone into as much detail as previous ones, so we don't know the state of the existing installation. We don't know the existing distribution board, etc., etc. But those are considerations that we need to consider with question 10. A bit later on. So, bit of information. I included or attached the data sheet that comes with Doncaster Cables, and a data sheet that comes with the charger, and also a link to the website for that charger. I've never installed one of those, but they look quite nice, that charger. I don't know if you installed one of them, Mark.
No, I think they're made out the Anderson charger is my rough understanding, but we've never had a go at one of those yet. But I do agree, they look really nice, don't they? Probably Lee and John, who will be from Artisan Electrics. I think they're in the chat tonight. They've probably installed one. But yeah, they look the business.
look pretty tasty, but again, within the installation instructions, etc., there are some key bits of information that we need to consider, obviously, as the designer. But the website's very good because sometimes you go into different manufacturers to obtain bits of information or to clarify certain things, because obviously we need to ensure compliance with the regs. But you can't find the information, or it's difficult to find, or it's quite difficult. But it was just luck that I chose it because I like the look of it. But the website and everything's very, very good. So you should have everything you need to enable us to be able to answer each question with a bit of luck. So happy days.
Good stuff. So we can see there that this circuit is buried in the ground. That's an interesting aspect, and you've set the distance for that as well. We'll see why that's important later on.
Yep.
Do you want me to scroll down a little bit?
Yeah, can do. Yeah, can do.
So we've got the TNCS supply, 230 volts, ZE of 0.14 ohms, and this is a 7.4 kilowatt EVSE.
That's it. Bit of information on distances of your cable run. So obviously you're going to need a total length, which we'll have a look at that a bit later on. Yeah. And then you've got your various questions, a bit similar to what you might find within your City and Guilds written examination or EAL even. I used to lay them out very similar to this. I presume, Dave did a similar approach, and Craig, did you lay your questions out similar, Dave, to this, or? Is he gone? It's gone quiet.
Me, sorry, I was muted. Yeah, I was working out. Yeah, so when you're posing them to people, obviously it gives a logical step by step to go through then in this manner, doesn't it? Like I think people often get confused or panicked with design calculations, and if you've got a method to apply and a routine that you kind of go through, then that is helpful when you're talking about sort of level 2, level 3 apprentices. Perhaps when you go down the other line of those in the chat that are maybe considering the 2396, and I think it's one of the examiner's biggest bugbears is that people seem to follow a similar routine and not have the deeper level of pulling apart the calculations. So it's kind of dependent where you're basing yourself at for what you're doing. But on the concept of apprentices tonight, which is what this is mainly for, then yeah, having that logical approach, starting with your design current, understanding your load, moving through your different factors, I think is a logical step in process to work on to give you a consistent answer, especially when you're looking at some of your online exams or some of your early calculations on site, working out with the other people as well.
Yeah.
So starting with the design current then, how do we come to that figure, Richard? Where do we get that from?
This is the quick sheet with all the answers in it. And as you progress through the answers, obviously, one stage leads into the next. And then what I've done is very similar layout to what we've done before, where we've listed tables and listed page numbers, etc., how to find the information and other considerations we might need to think about. So again, simple design process. We want to calculate our design current, and again, we're working from the old formula that most of us are familiar with, PIV. So to calculate current, we need to divide the power by the voltage, and if we've got a power factor to think about, we need to multiply the voltage by that. But in terms of this piece of equipment, this charger, there isn't a power factor to consider. So it's a nice simple calculation. And this charger actually, when you look at the manufacturer's technical information, it actually runs at 7.4 kilowatts. So 7.4 kilowatts, 7,400 divided by 230 will give us a design current of 32.17 amps. Happy days, nice and simple. So our design current, we've worked that out quite nicely. Although within the questions, I haven't talked or spoke about diversity. We have spoken about it in other podcasts, in other cable calculations. So can we apply diversity in terms of an EV charger? Well, when we look at the regs and we look at the code of practice for installing EV charging equipment, it does state when considering the additional load to be used for EV charging equipment, the rating of the equipment is used in assessing the additional load. So actually, we cannot apply diversity to it. So if this charge is going to take 32.17 amps, that's what it's going to take. However, when we go into section 722, which is, of course, back of the regs book for any special installations or locations, there was a bit of a caveat added in Amendment 1 in 2020 when that came out. 722.311.201 and it talks about maximum demand and diversity, and it talks about load curtailment, including load reduction or disconnection. That can either be automatic or manual. You may be able to take this into account when determining maximum demand of the installation or part thereof. So basically what they're saying is, if we've got a way of controlling the load, whether that is either by disconnecting it, presetting it inside, or whether it's got an electronic automatic way of doing it, maybe via a CT clamp or something, then we can take that into account. And if we know that, for instance, we've got a 60 amp supply and our existing demand is 30 amps, but we're going to be adding another 32 amps, we can tell the charger that actually we've only got a 60 amp supply. The charger will then automatically adjust the charge rate, so you'll never go over the maximum rating of the supply coming into the property.
If you're really lucky, the DNO can do that for you, just to chuck that in there.
And go on, Craig.
Isn't this part of the DNO's sort of wider plan? And some people in the chat will be doing this far more experienced than what I am, because I'm not installing chargers, but with the whole concept of bringing in, having to have access and metering and being able to see what people are doing to sort of control that on a sort of wider and more national basis. And be interesting to see what people are doing on those installs as to how much this is actually being applied to those situations and how much stress, I guess, they're getting off the DNO to kind of enforce any of that and do the load monitoring to make sure that it has been allowed for currently, or whether it's just one of those stories that they say they'll do in the future, but they don't actually check very often.
Yeah. So we have got the facility to be able to do that. It's another bit of kit we need to buy, but certainly this manufacturer, this charger, does offer that facility. So I don't need to worry too much then about maximum demand, because I can set it via my CT clamp, etc. But otherwise, we cannot apply diversity. So if we did have 30 amps existing, which isn't a lot, 32 amp charger, wouldn't be able to install it. We'd have to either reduce the charge rate manually or something, or we'd be in trouble. So it is something to consider. So we calculated our design current, and the next thing we're going to do is think about the rating and type of the overcurrent protected device, and we've also got to consider any additional protection if required. So when we look in chapter 43 of the regs, it talks about overload protection, and it gives us this formula: IN should be equal to or greater than IB, which should be equal to or greater than IZ, etc., etc. And that is regulation 423.1.1. So we're going to apply the next few parts of the calculation into that formula to make sure that we are compliant. So we don't know the make of the board, etc. I haven't given you that information, but what we need to figure out is what type of protected device we need it, and do I need to consider additional protection. So we're probably going to be selecting either an RCD or an RCBO, but we know that the overcurrent protection is going to be provided by the MCB. So we don't know if there's any inrush current for the charger. There's nothing declared in the manufacturer's instructions. I've had a look. So we don't know the rating of the device yet, but we're going to select that in a minute. But we're definitely going to have a type B. And for those that aren't sure about the different types of MCBs, there's a very useful table in the on-site guide, 7.2.7, indent 2 on page 90, that talks about type B, type C, and type D MCBs. But we have got to consider in the regs on page 327, 722, 531.3.101. So it says, unless supplied by circuit using a protective measure of electrical separation, each charging point incorporating a socket outlet or vehicle connector complying with BSCN 621.96 shall be protected individually by an RCD type A, F, or a B, and have a rated residual operating current not exceeding 30 milliamps. So it does need additional protection as well. Except where provided by the EV charging equipment, protection against DC fault current shall be provided. So we either need a type B, or we need a type A or an F, but that needs to be used in conjunction with a residual direct current detecting device, an RDC-DD, complying with BS IEC 62955, as appropriate to the nature of the residual and superimposed currents and recommendation of the manufacturer of the charging equipment. So what does this charger have already built in? So I've highlighted or copied a little bit of the information just there under safety and protection systems. It does have a built-in RCD, and it is a 30 milliamp type A, and it has got a 6 milliamp DC RDC DD device built in now. When we go back to 722.531.3.101, just above there, it says any RCDs shall comply with one of the following standards. Unfortunately, that RCD that's built into that charger is an electronic type of device, and it doesn't comply or conform to any of those standards because it's not listed. So therefore, we are going to have a type A device upstream. So therefore, we're obviously going to select an RCBO, aren't we? So we need the rating of our protected device to be equal to or greater than 32.17 amps. The next size up is going to be a 40 amp device, and we need a type A RCD. So we're going to be selecting a 40 amp 61009 RCBO with a type A RCD.
Rich, can I jump in there just quickly? I was just going to say one of the common occurrences that I found, and I'm sure you have as well, in education, and it was this misinterpretation of what you've just quoted, the relationship between IB and IN. We're just over the limit of a 32 amp protective device, 32.17. One of the common misconceptions is if we were bang on 32, what some of my learners used to do is they still used to go up a size. If it was for a standard circuit, obviously we're looking at car chargers here as continual current use, but it's just a little tip for people who are watching now and might be watching later on, that it's equal to, it can be equal to as well. It doesn't have to be over. So if you've got something that was 32, you could use a 32, just as an example, because it's a common error which occurs when you're doing cable calcs.
But we're at 32.17, aren't we? So it is.
Yeah, so we're and I'd say it's a different scenario because we're using a car charger as well, so that's going to be continual load. I'm just talking about your more sort of traditional load, your cookers, your showers, and things like that. If your design current was 32 or 40, you can be level with it as long as it's not, your design current's not over that protective device rating.
Yeah.
And so one of the manufacturers recently said to me that if you're staggering your RCDs, we would normally approach it if we had a type A downstream of a type, you'd have a type B upstream to that. And because some of these EVSE charge points, whilst they're not mechanical RCDs in the way we understand them, they still do kind of try and define them as type A. So my approach has changed of late, where we'll use a type B now up front to some of those with the electronic RCDs in, but you don't have to do that. It's just something that I think is good practice. With the way you would use selectivity in terms of staggering out your MCBs, RCBOs, doing the same with the actual type of the RCD as well. That was something that I've forgotten his name now, but it was a gentleman from Proteus told me about that. So something to keep in mind. And Neil's dropped a question in the chat saying overcurrent protected devices to protect the cable, not the equipment. And that absolutely is kind of, yeah, I'll let you carry on with that, Richard.
Yeah, that's okay. Yeah, absolutely. So going back to fulfill the requirements of section 43, then IN should be equal to or greater than IB. So our design current was 32 amps. Our protected device, therefore, is 40 amps. If we'd have stuck a 20 amp, for instance, protected device in there, ultimately the 20 amp device is going to think that, you know, the cable's going to set on fire because it's been overloaded and it will trip due to overload. So of course, bad design. So far we've got our design current, calculated that.
So
our protected device. Go on, Craig.
Sorry, just before we move on from that, there is obviously other considerations with the RCDs around the charger that we would have to put in place that maybe wouldn't be considered with other RCDs, isn't there, about the fact of them being double pole or switch neutral or whatever way they're talking about it now, about them needing to
That's question
disconnect.
10. That's question 10.
Oh, that further down, is it? Sorry.
Yeah, other considerations that you've got to think about. We'll come back to that bit. There's a bit of a caveat at the end there to have a look.
Ahead of the game. Ahead of the game.
And similarly to what Mark has said in terms of your different types of RCDs and where you can have them or where you can't, where you shouldn't because of DC leaking back through the installation and all that type of stuff. What you can have upstream and downstream. But again, we'll come back to that in question 10. So happy days. So we've got our design current and we've got our rating of our protected device. So we're going to use a 40 amp 61009 type B RCBO with a type A RCD. And of course, to determine what type of RCD, we've got to have a look at the symbol on the front of the devices. So I've tried to include your little symbol there for an A and what symbol you'd need. If you didn't have an RDC-DD device built in, you'd have to use a type B. But historically, type B RCDs are rather expensive. Is that correct, Mark?
Just a little bit, yeah. They're coming down ever so slightly in price, but very much so.
Yeah, never bought one, but they are quite expensive. Okay, so next then we're going to determine what our installation or reference method was. So within the question it says, for part of the run, the cable is fixed directly to the masonry wall, which of course would be clip direct, fixed direct, reference method C. But for most of it, it's buried directly in the ground, which would be reference method D. So we've got to consider which method would have the worst effect on the current carrying capacity of the cable. And of course, try to draw a few arrows on that, try to illustrate the cable trying to dissipate heat. And of course, you know, the worst case here is the cable that's buried directly in the ground. So the reference method we're going to use is reference method D. And I've copied that information directly from table 4A2 of page 437 of the regs. There is a number there, 72. And remind us what that number was for, Craig.
So when you've got these tables, you've got a difference of an installation method against a reference method and them having the two different variations, so that if you've got a couple of different options of, say, bunched in containment, for example, there's different ways in which cables can be bunched inside containment. So you need to look at the installation method to determine the difference between B for bunched, as we always used to talk about in colleges, being a very simple overview level of it, when actually there's quite a lot of methods of containment where they could be bunched together.
Yeah, for instance, number 73 is very similar to 72. It's still reference method D, but it's where you've got a sheath armored or multi-core cable directly in the ground, but where you've got additional mechanical protection over the top. So it'd still be reference method D, but when you look in the regs, it's actually installation number 73. But in terms of what we're looking for here, the reference method is D.
Rich, can I just drop another tip in there? Just for those who may be involved with inspection and testing, another common error where you've got 2 or 3 even reference methods within the installation. In this one, it's clip direct and then it's buried in the ground. The common error for people doing certification, they put more than one reference method in the box when they're filling the certification. So you always go with the one that has the most adverse effect on a cable, so which has the most detrimental effect. And in this case, it would be D. Yeah, a D reference method is going to affect the cable and its current carrying capacity more than if a cable was clip direct. So I know it's not necessarily a design tip, but it's just for those who may or are thinking about getting involved with certification and inspection and testing. Thanks, Rich.
Absolutely. Especially if you was designing this, you were signing the design part of the cert, you were installing it, so you signed the installation side. And if you was then verifying it, again, you're going to need to fill out the certification. And of course, you don't want to get the information incorrect on the cert if you're signing it. So good point, Dave. Good point.
Yeah, okay, I almost need to add a box to the set for putting down these different numbers when you talk about bunched and things. Don't need to have what method of the installation were you actually using at that point.
I agree, Craig. There's too many variances, as you've pointed out. So yeah, I totally agree with that.
I suppose we could record it in the remarks section. We could add, an additional bit of information there, couldn't we, to reference that? Why not? Remember that the model forms in the regs are only a starting point. They're a minimum amount of information that's required. You can always add to it, which is a good idea. Okay, so next we've got to consider now then any derating factors that are going to affect ultimately throughout the cable's run its ability to carry current, basically. So what derating factors do we need to consider? So when we look at the drawing, we know that we've got an ambient ground temperature to consider of 25 degrees C. Cable's actually buried in the ground, so we've got to consider the effect that that's going to have on the current carrying capacity. It's buried at a depth of 0.5 metre, and of course, depending on how deep it's buried and whether it's in a duct or not in a duct, etc., that's also going to have an effect. and the soil that it's actually in, because it's not in a duct, it's direct in the ground, depending on the resistivity of the soil, that will also have an effect on the current carrying capacity. So a nice little example really, where we've got 4 different factors or correction factors that we've got to consider. So what we've got to do first of all then is to use the information in the question and go to the relevant tables, and most of the information we're going to need is in Appendix 4 of the regs, unfortunately. A lot of this stuff is not in the on-site guide, so we've got to use the regs for this one. But I have highlighted and listed the table numbers and the pages, so if you want to follow along with that. This,
I
of
think
course,
my picture will be too small now, but that's kind of a shot of one of the tables from the regs, and yeah, they are linked in the answer sheet that Richard's got there. So go off and check those out and just hunt through the appropriate ones and choose your numbers.
I'd have screenshotted them and put them in, but I just run out of time today. But
we'd get done for copyright anyway, mate. We don't want that on our case when you boys are from ESF. Let's not go there.
So if we look in table 4B4 on page 442, we're looking for, and we've got to select with any table, we've got to use the right columns, etc. And it's in relation to, we've got to go up one, sorry, Mark.
Yeah, sorry.
Sorry, mate.
So you got your ground temperature of 25 degrees Celsius.
So we've got 2 tables to consider on page 441 of the regs. Table 4B1 is for ambient air temperature. But we haven't got an ambient air temperature to consider, it's ambient ground temperature. So 4B2, we've got the ground temperature on the left from 10 degrees up to 80. Then we've got to consider, or we need to know what the rating of the insulation is on the cable that we're going to be using. So this is kind of where we've got to go back now to the Doncaster Cables technical sheet. We need to have a bit of a look at that, because this is important. And when we go down or up, it should go right the way to the top. There we go, all the way up, all the way up, all the way up. There we go, there it is. So insulation, thermosetting, XLPE. So it's thermosetting 90-degree insulation. So if we go back to our table 4B2, we're going to go down the left-hand column, 25 degrees ground temperature. We go across to the 90-degree thermosetting column, and we've got there a factor of 0.96.
Rich, can I jump in again?
Yeah, help yourself. Yeah.
Sorry to be a pain. Another little tip for those who are watching. We know on the panel from experience, XLPE cross-linked polyethylene is 90-degree rated. If you see that on a data sheet, as you've just seen, it doesn't necessarily say 90-degree or 70-degree. It will say thermoplastic or thermosetting. So for those who are watching, if you ever see the abbreviation XLPE, it's always 90 degrees, but just check whether it's thermoplastic or thermosetting with your manufacturer's data, as Richard did. We take it for granted that XLPE is 90 degree, but just if it's not XLPE, it's going to be 70 degree.
I think to not get caught out, not jump ahead in case it's further in here as well, but people being aware that even if the cable's at 90 degree, if the manufacturer's equipment isn't saying that they'll handle 90 degree, then that last 20 degrees is almost irrelevant, because you need to be calculating at 70 degrees as a cable rather than 90 degrees, because of the fact that the manufacturer's equipment won't guarantee it can take that sort of current. So don't be thinking, oh, well, if I buy this one instead of that one, I can get extra sort of current carrying capacity out of this, because it won't work that way in the application, fortunately.
Yeah, I think what we'll probably find is that someone's made a mistake along the way, and they've perhaps used the wrong table with what you pointed out, but it says in note 1, as Rich will point out
We'll see that in a minute.
And if you're using electrical OM, there's a handy button in there for 70 degrees, as my good friend Neil Bridgman pointed out to me when the first video I shared doing a design using it didn't account for that. So cheers, Neil.
You can set that as a default so you never miss it.
I've done that now.
And by 90-degree thermosetting insulation, what are they saying, Dave, with that? What's the idea of that? What does it mean?
It's all to do whether it can be reworked and reshaped. It's the properties within the the sort of makeup of the insulation itself. So you can tell off if you're unsure, you can tell off the BS number printed on the side of the cable as well. Typically BS 5467 tends to be XLPE thermosetting, but always check. The one thing with these, I've done it myself. I'm going to hold my hands up. Richard, give me this question to look at today, and trying to rush, I myself made a mistake. So I'm sure as we go through, you might find you've made a little mistake somewhere. But just when you do cable calcs, as what Richard's done as a suggestion, make a note of the table, the page number, the table you've used, the column, and you can easily see where you've gone wrong. And you might not have to start again from the top. You could start sort of part way through. So just with this question, it is a particularly tricky one. He hasn't used, your particular rating factors that we normally find. We've used some not out of the ordinary ones, but normally cable calc questions. It's normally insulation grouping and thermal insulation grouping and ambient temperature. But this is quite a tricky question. But kudos to those who've got to this point. And if you get to the final answer, fantastic.
And if this was part of your qualification, so maybe a question within your design unit or something, you would get marks for listing tables and writing formulas down. You might
even if your final answer's wrong, like you say, it might be a 10-mark question. You might end up with 8 marks. It might just be your final answer's wrong. But if you can see exactly where you've been, the more information you put down, the better. Especially if you're looking to do the design qualifications and written exams. Perfect.
So I was going to say, having just done the 2396, one thing that was hammered in very heavily was the fact that it might give you 3 marks for working out, say, a derating factor, but actually putting down 0.96 is only getting you one of those marks. It's expecting the other mark to be about the table and the reference and in the column that you've chosen and justifying your reasons. And they actively say, don't they, that even if you've got the figure wrong, if you've listed everything else right and you've carried that on through the rest of your calculation, after the first figure you've got wrong, they will give you the marks for sticking with that all the way through, and as long as it's referenced and laid out properly. So there is merit in the way this has been laid to make sure that you're getting the marks you deserve, even if you make a slight error.
And I agree, and even little things like it complies, it does not comply. That could be a mark in itself. You just put a number down, it doesn't mean anything. So for those who enjoy this type of stuff and maybe looking at doing this as an additional qualification, the more detail it does comply, it does not comply with things like volt drop and adiabatic equation and things. Fantastic. Just put as much information as you can.
But even for those doing apprenticeships and stuff, I don't know about you gents, but when they're doing their inspection and testing, I want them to be putting on their sheet that they've checked against the on-site guide or the regs or whatever and confirmed the ZS is actually complied, rather than just putting the value in. I want them to evidence to me on their apprenticeship that they understand that that's what it means.
Yeah, exactly.
Good stuff.
Absolutely. Yeah. Okay, so we've considered the ambient ground temperature, and we've got a factor for that. Because the cable's buried, when we look in Appendix 4 of the regs, Section 4, it's all about overload protection. And it tells us within that Section 4, overload protection, the bottom paragraph talks about the tabulated current carrying capacities for cables direct in the ground or in ducts in the ground. So that applies to this scenario here. Anything given in this appendix are based on an ambient temperature of 20 degrees. The factor of 1.45 that is applied in regulation 433.1.1 when considered an overload protection assumes that the tabulated current carrying capacities are based on an ambient temperature of 30. So to achieve the same degree of overload protection where a cable is in a duct in the ground or buried direct, as compared with other installation methods, a rating factor of 0.9 is applied as a multiplier to the tabulated current carrying capacitor. So because this cable's in the ground and it can't dissipate the heat as quickly as a cable that may be clipped direct, we've got to consider that because that cable is going to get hotter quicker. So it's telling us that we need to apply factor, CC, of 0.90. And we can find that, as I say, page 424 in Appendix 4 within Section 4 towards the bottom of that bit of information. 0.9. That gets missed quite a bit, to be fair. And the reason is because it's in the ground, regardless of the soil and everything, it's going to struggle to dissipate the heat. So that's CC. Go on, Dave.
I was just going to say, I think another reason why this gets missed as well, and it was a common sort of complaint from my apprentices, is not all the rating factors are together. They're all spread out across a range of pages. And it might have been probably the most difficult one to find for those who've attempted the question, whereas ambient temperature and grouping, etc., are all within a certain set of pages, aren't they? I'm not sure as to why they're spread out as they are, but it would be much easier. I was always in agreement with my apprentices. It'd be much easier if they're all in the same section rather than bouncing around loads of pages.
Well, if it was that easy, you wouldn't have plumbers and carpenters and all that. Do you know what I mean?
One thing I've always got them to do is, because you're allowed to make small annotations in your regs book, right? So one thing I've always got them to do is on page, is it 420, where you've got the start of Appendix 4, where it lists all the different factors. I get them down the left-hand side to write the page number where each of the tables and each of the factors are, so they've got a quick navigation point as to where they're looking, because the amount of students that go, oh, but I looked at this table and it gave me this value, and it's like, yeah, you looked at the 70-degree armoured, not the 90-degree armoured, therefore you've looked at the wrong table. And a
highlighter pen as well to bring that information to your eyes as you're looking through that book is, you know, worth its weight in gold. So I've got mine highlighted, and it's a suggestion I've always made. So, but yeah, I agree.
Okay, so we've considered two of the rating factors. The next one to consider then is depth of burial, CD. And again, we've got to go now to table 4B4 on page 442. And we know that this cable is buried from the information in the question at a depth of 0.5 metre. So I'm going to look in table 4B4, rating factor CD for depths of laying other than 0.7 metres for direct buried cables and cables in buried ducts. So quite a simple table to use. We've got to look on the left-hand column to find the depth, how deep it is. So we know it's 0.5 metre, but is it buried direct or is it in a buried duct? Well, we know it's buried direct. So therefore, our factor for 0.5 metre buried direct is 1.03. Happy with that?
Happy with that?
Yeah. I could have chose 3 metres, but he didn't want to dig it that deep, so he just went
definitely not if I'm digging.
Just to throw a curveball in there, what do the regs state about depth of cables? Is there a specific depth?
I don't think it defines a depth within the regs. So they just say to a good engineering depth. I know that the DNO use 600 mil. That's what we've always done since day dot with my job, because I work alongside the DNO, so it's just what we do. But yeah, I think it's one of those. Depends what's on top of it, I guess.
Yeah, it's true. It just states a sufficient depth to avoid mechanical damage. It's a common question I used to ask adult learners doing the 18th edition, and 9 times out of 10 they'd say, "Oh, it's 450 mil or 600 mil or a metre," but it doesn't actually state unless it's in agricultural installations.
That's right.
It's a 1 metre.
Caravan park, special installations where you've got potential of people driving in stakes to hold your tent down or equipment, things like that.
So I just thought it was worth putting in there because there isn't. It doesn't actually state a specific depth, but obviously we need to be sensible and look at the routing if it was a real job, and look at the potential of mechanical damage, hazards, things like that. So 0.5 metre, I think, is a suitable suggestion in this particular scenario.
Yeah. And then the last one we got to consider is the resistivity of the soil, CS. Now for this one, we've got to go to table 4B3 on page 422. So just above table 4B4, we've already looked at here. And we've got a factor that's been given to us within the question of 3km/W, whatever that stands for, because I'm not sure. Somebody else might know. But we've got a value of 3 then, so we need to look within table 4B3, and we've got 2 columns to decide which one we're going to use. So rating factors for cables in buried ducts is the first one. Well, it's not that. rating factors for direct buried cable. So looking at the bottom one, we're going to go all the way across till we get to 3, and we've got a factor then of 0.90.
The KMW, I can't remember the exact meaning of the word. I haven't got my regs book in front of me, but basically it comes back to the different types of soil and the different types of ground that can be applied come back with different factors.
Yeah.
And when you look at it sits under a different standard, but when you look at the reference methods as far as cables buried in ground, you get cables buried in ground and you get cables buried in ground with an ERA reference method, which the ERA reference method's a little bit more forgiven to do with how dry the soil is compared to how wet the soil is and the values that it gives then for the current carrying capacity that it's able to factor in. And there is a table in Appendix 4, which I don't have to hand, that talks about different soil resistivities and the depth of cable from what you were saying before. Although there's not a sort of a minimum depth, there is a value that gets applied on them, which can be used if you apply in a slightly different reference method to the ERA version, which will give you better values on your cables. But there is rules around being able to do that, such as it's got to be covered in type 1 rather than just soil, for example, to be able to apply that reference method to it. But I'll dig out the other information. I only know that randomly because I had to use it on a job which made a difference in cable size quite considerably. So I'll post that in the notes or whatever for once I've got my book and can sort of dig it out. But I can't remember what the KMW stands for, but it's to do with the soil thickness or dryness or type or something, I believe.
Okay. But ultimately, they're going to affect the cable's ability to dissipate heat, aren't they? That's basically what it all is. You combine them together, and it's going to have an overall effect, and we need to allow for it. So we've got 4 factors to consider. Now, we've given a formula, and within Appendix F of the on-site guide, it breaks down the formula itself, but also within the regs, page 425, we've got a number of different formula for calculating IZ, which is the minimum amount of current that the cable should be able to carry for continuous service. So it gives us a formula of IN, which is the rating of our protected device, which we've already chosen prior. And we need to divide that by all of our correction factors multiplied together. So 40 amps on the top, we need to divide that then by our 4 different factors. So CA, 0.96, CC, 0.9, CD, 1.03, and CS, 0.9. So now we need a cable that can carry, because of all these different factors that have had an effect on the cable to dissipate heat, we need a cable now that can carry 49.942 amps. So really, if you round that up, we need a cable that can carry about 50 amps. Okay, happy with that?
Yep.
So what we need to do now is select the right cable or the right table for the cable. So as Craig alluded to earlier, the cable we know is 90-degree thermoset in the cable that we're going to be using. However, when we look in table 4E4A in the regs, there is a note by the side of it that states where it's intended to connect the cables in this table, 90-degree, to equipment or accessories designed to operate at a temperature lower than the maximum operating temperature of the cable should be rated at the maximum operating temperature of the equipment or accessory. So this cable, in effect, can carry or can cope with 90 degrees all day long. But the equipment we're connecting it to, now we know one end's going to be connected into the EV charger, the other end, maybe the DB, we're not sure. But that equipment would also need to be rated at 90 degrees. If it's not, we can't use this table. We're going to have to use the 70-degree table. Is that about right? Have you had some experience?
Can I jump in again, Rich? I can't stress to everyone who's watching this how important that note is there that is highlighted on screen. So if you've got your regs book in front of you, highlight note 1, which is to the right of the table for current carrying capacity. Craig pointed it out earlier on as well. This is such it's so important, and it's a curveball that's threw in quite a lot in questions in written exams. And what they're trying to do is they're trying they're not trying to trick you or trying to trick you up. They're trying to see whether you've got that level of knowledge there, whether it's just sort of surface learning or you've got that deeper level of knowledge. And they'll always try and put something in with a 90-degree cable in the hope that you're going to select that table. Yeah. So if you've got your book open, highlight that note now as it is.
Page 464, that table's on. Page 464.
464, highlight the notes to the right. And the reason being is the majority of equipment that we connect to is only rated up to 70 degrees. So although the cable's 90, we cannot use that particular table. So it's it's probably one of, or if not the most important point. If I was watching this as an apprentice now, that'd be the most important thing to take away from this session today, 100%.
So because we can't use that 90-degree table, we've got to use a 70-degree table, and we'll find that on page 454 in the regs book. So table 4D4A. So this is multi-core armoured 70-degree thermoplastic. So 70 degree. So based on that table, then we've got to consider first of all the reference method, and is it single phase or 3-phase? So reference method D, we're going to go all the way across to the right, and we're going to use column 6. So on the top of your reference methods, you've got numbers. So column 1 is the cross-sectional area, column 2, reference method C, etc. So go all the way across, column 6. So reference method D, 1 2-core cable, single phase AC or DC. We need to go down that column 6, until we come to at least 50. So we can't use 6 mil because that will only take 46 amps, but we can use 10 mil squared because that will take 60 amps. That makes sense?
This is the point where it could all go horribly wrong, isn't it, Rich? If we've used the wrong table.
Absolutely, yeah.
From this point, the rest of it could be wrong, the values, but at least if you're putting in what tables you're using and column references and page numbers, you still might pick up some marks. So all is not lost, but it can one sort of error by perhaps rushing a little bit, not paying particular attention, could have a huge knock-on effect to the final outcome. So just tread carefully sometimes, and just be careful with what tables and columns that you're using.
Okay, so we know we need a cable that can carry at least 50 amps, and using that table, we're going to select 10 mil at this time because that will carry 50 amps. Happy with that? But like we've done in previous cable calcs, have we actually overlooked anything? Well, we've got a variation to the formula we've just used, where we can use the design current to divide our correction factors in, as opposed to the rating of the device. You find that information and the formula in Appendix 4 on page 425 in the regs book, and it says alternatively, we can calculate or find out how much current our cable needs to carry by using the following formula, provided the circuits of the group, if they're grouped or on their own, are not liable to simultaneous overload. So we've got to consider, can this 7.4 kilowatt charger ever overload? Can it ever draw more than what its maximum it's rated at? It can't. So
it shouldn't be able to. No. I don't trust electronics.
So we've got another formula that we can use, and what we've done is we've changed the IN value for our IB value, our design current. And how does that affect then the amount of current that our cable needs to carry? Well, instead of it having to carry 50 amps, we need a cable now that only needs to be able to carry 40 amps. So if we go back to our table, current carrying capacity table, instead of looking for something that can carry 50 amps, so column 6, reference method D, we only need it to be able to carry 40 amps, so I can actually select a 6 mil cable. So 6 mil will do it all day long. The correction factors haven't changed. It's just that the piece of equipment that we're connecting to, it can't overload. So it gives us an alternative formula whereby we divide our correction factors by the design current, because the design current can never change. So you can't overload the cable because it can only ever draw 32 amps. How does that, transpose out? Well, actually, we can select 6 mil now.
Just to add, I'm going to be totally honest here with everyone watching. I've looked at this afternoon because I wanted to check it for myself. And at this point, this is where I actually went wrong. So everyone makes mistakes. And I think what we do is so used to following a process with cable calculations, IB, IN, gathering your rating factors. And sometimes we can miss something such as this. So the formula has only changed slightly because we're using the IB value rather than the IN value. But we can see we've had a major change, and it could be a real cost, have real cost implications. If I was calculated, I was using a 10 mil, but with Richard's variation, considering that we don't necessarily need overload protection, because if the charger says it's 7.4 kilowatts, it's not going to suddenly jump up to 10 kilowatts. Richard can use a 6 mil cable, and therefore it's going to be cheaper, to the client. So it's so easy to be following that process and miss something as I did, and I'm going to be totally honest and say that I made a mistake. So there we go. Over to you, Rich.
You could use 10 mil. You cite it, but you could use 10 mil. I mean, I don't know.
Yeah, you could do, but it might be the difference between if we're having this job to tender, you might, I might not necessarily get it because my cable's too expensive. But it's just to point out to people watching that a simple mistake can have that knock-on effect again. And majority of people might not be aware that alternative calculation can be used. We're so used to always putting the IN over the rating factors in a lot of examples, but equipment that might not necessarily need overload protection, where it's a fixed rating. So cookers, showers, EV car charging points, they're not going to suddenly use more than what it says on the tin. So if you've got an 8 kilowatt shower, it's not going to suddenly pull more than 8. So you could use that formula as an alternative. So again, a key point there.
What about if we've got a distribution circuit though, Dave, with multiple loads?
Yeah, obviously we can't, can we? Because we don't know what's going to be connected. So we'd always use the IN rated over the.
It does give us a caveat that where they are not liable to simultaneous overload, where you couldn't guarantee that, could you?
Yeah.
Whereas a single piece of equipment, if it's rated at a value, it can't overload. Simple as that. So it's quite useful, but it saved us a few quid there.
Yeah.
And still fully compliant with the regs, because it gives us that alternative formula. I haven't made it up; it is there. So far we've done IB, we've done IN, we've done IZ, and now we've got IT, which is the tabulated current carrying capacity of the cable, and we've chose 6 mil because it will basically take 46 amps continuous all day long. So pretty good. What we need to consider now then is to verify that the maximum volt drop based on the length, the type of cable, size of cable, etc., design current isn't exceeded. We need to confirm that the 6 mil is indeed adequate for it. So information on calculating volt drop and volt drop information is again within Appendix 4 on page 428 of the regs within section 6. And it gives us a formula, but it gives us it in words, whereas in the on-site guide, it actually gives us the formula written out. But as Craig's already said, there's no reason why you can't handwrite the formula out. It's not really a problem. And it tells us to calculate the volt drop then, we'd need the millivolts per amp per meter value for the cable we've selected. So we're going to have to go to a table and find that. We need to multiply that by our design current. We know what that is because we've already calculated that at 32.17 amps. We need the total length of the cable. So we're going to have a look back at our drawing. And because the value is given to us in the table in millivolts, we don't want that in millivolts because the maximum we're allowed is in volts. We need to convert it back into volts. So we divide that by 1,000. So the first thing we need to do is to establish our millivolts per amp per meter value for our 6 mil 70-degree multi-core cable. So to find that, first of all, we're going to go into table 4D, 4B. So these current carrying capacity tables, you'll find that the millivolts per amp per meter values always follow in the table underneath. So on page 455, we've got table 4D, 4B, and this is the volt drop per amp per meter values for multi-core armoured 70-degree thermoplastic. So we chose 6 mil. So we're going to go down column 1 for our different sizes of conductor, down to 6 mil. We're going to go across then to our column 3, which is our 2-core cable, single phase AC. And that gives us a value of 7.3 millivolts per amp per meter. So basically, for every meter of this 6 mil cable, we're going to lose 7.3 millivolts. Okay. We need to times that. Go on, mate.
Sorry, I'm going to just come in again because another error what people may do is you've put at the start that there's going to be an integral CPC into this armoured cable, and sometimes I've had some learners they pick it's 3-core rather than 2-core because they think, well, I've got my line, my neutral, and my earth and my CPC. However, your volt drop is only affected between your line and neutral, isn't it? Because there's no voltage on the CPC. So it's just another tip, really. You know, you never count the earth or the CPC in any circuit when you're looking at volt drop. And don't be put off by the formula either, because it looks complicated, but the MV/AM value is just one number out of a table. So then you need your IB, which you've already worked out, and the length you've probably been given in the question. So don't be put off by the formula because it's not as technical or as difficult as it first may seem.
So as Dave said, we've only got to put the information into the formula. We do need to calculate our total length. So if we scroll back up to the drawing.
So a lot of the time it's given, isn't it, Richard, in the question, but obviously on this one, we've got a nice diagram and obviously just a little bit of working out, simple addition there.
So we've got 2.6 meters. We've got 1.4 meters, so that'll be 4 plus 22. So we've got a total length of 26 meters. Happy with that? So we can go back to the calculation. Tell you what, you're getting good at this, Mark.
I'm trying. It's hard work.
7.3 times 32.17 times our total length, 26 meters, divided by 1,000, because again, we want the answer in volts, not millivolts, gives us a calculated volt drop then of 6.1058 volts, 6.1 volts. The maximum volt drop we're allowed, we've got to go into the regs and have a look at table 4AB. And it talks about in table 4AB, whether you've got a supply from the public distribution system or your own private supply. So we'll just go back and find my table. Just want to have it left there. So on page 430 in the regs book, table 4AB, and we're given a maximum percentage of volt drop on lighting or other uses. This isn't lighting, it's other uses. And it's given to us at 5%. And it says the calculated volt drop should include any effects to harmonic currents. You've got to consider that. We don't have any harmonic currents in this one. And it is calculated and expressed with respect to the value of the nominal voltage. In other words, line to earth. So we're basing it on 230 volts. So 5% of 230 volts equates to 11.5 volts maximum. Our calculated volt drop of 6.1 is equal to or less than 11.5 volts. So that 6 mil cable is more than acceptable and more than compliant with the maximum of 11.5. So far, our 6 mil cable is looking pretty good. Happy with that? So far, so good.
Doing good, Richard. Are we ploughing on for a bit? I don't know how much further we've got to get through. Should we just press on a bit longer?
Can do if everybody's happy. So I'm okay with that. No problem.
Yeah, I'm happy if you're happy, mate.
Yeah, okay. All right. So next thing we're going to do is verify our shock protection. Now, if our chosen protective measure against electric shock, and there's a number of them listed in chapter 41, is ADS, automatic disconnection of supply. In order for our protected device that we've chosen, i.e. 40 amp type B RCB over the type A RCD, in order for it to disconnect within the maximum time allowed, we'd need to have a certain amount of fault current generated to disconnect it within the required time. So, first thing we need to do is consider, and this is going to be quite an interesting conversation, what our actual maximum disconnection time is for this type of circuit. So, within the regs book, page 64, 65, in chapter 41, if we have a look at regulation 411.3.2.3, and I've made a note of it there, find that on page 64-65, talks about maximum disconnection times that are stated in table 41.1 shall be applied to final circuit to the rated current not exceeded. So the first thing to consider is our circuit to our EV charging point a final circuit, or is it a distribution circuit? If we're unsure about what a final circuit is, remember that we can always go into part 2 of the regs, because that gives us our descriptions, basically, information about what the various symbols and abbreviations and language that's used in the regs, but it explains it to us. So a final circuit within definitions, part 2, is a circuit connected directly to current using equipment or to a socket outlet or socket outlets or other outlet points for the connection of such equipment. So it does apply to our circuit. It is a final circuit. Now, is it a piece of fixed equipment, or does it incorporate one or more socket outlets? This is the question. So, before we get to the maximum disconnection time, I've included a couple of bits of information here out of the regs book to try and clear this up a little bit. So, when you look in 722.55.101, it talks about socket outlets and connectors. So we've got a number of options there that our AC charging point shall incorporate. So we've got a number of options. One of them is a type 2 socket outlet or vehicle connector. Okay, and it does say in a note there, vehicle manufacturer's instructions should be taken into account when determining the type of socket outlet to be installed. So I think underneath that, I've included a little bit of information from the manufacturer. So Mark can go down. You're right, mate.
Let's scroll down.
There it is. So it says connection type 2 socket, and there is the bottom of the charger, and it is a type 2 socket outlet. Definition of a socket outlet in part 2, I've included that. A device provided with female contact which is intended to be installed within the fixed wiring and intended to receive a plug. So would you say that the socket outlet on this EV charger is a socket outlet, or is it a piece of equipment?
Go, Craig, he's got his hand up.
What do you think, Craig? So we'll have to go back.
My question comes back to, well, is it tethered or untethered? Obviously, in this scenario, it's untethered, but does it change? Because when you look in the code of practice, the pictures denoted in there by the IET show that one that's untethered, they clearly state has a socket outlet on the charging equipment, whereas on the tethered, they class it as a vehicle coupler rather than a socket. So based on what charger you're installing, does that potentially change the definition as to what it is for its disconnection times? Or does it not matter anyway with an RCBO protecting it?
No, but would you say in our scenario, it's a socket outlet in this one?
In this example, I would say it's a socket outlet because it's got a socket connector on it because it's untethered.
In such case, then, we're going to assume that we've got to use table 41.1 because table 41.1 you've got to use if you've got socket outlets up to 63 amps. And of course, ours is rated at 7.2 kilowatts, 32 amps or so. So therefore, our maximum disconnection time when we look in table 41.1 for a TNCS system is going to be 0.4 seconds. Okay with that? So back up again, Mark, sorry.
And just to say, Neil Bridgman's dropped in the chat that BS7671 states that an EVSE is a socket outlet. I think it's probably just a hangover in some of the language that's used in the book, isn't it? Whether it's been tethered or untethered. You'd imagine the application either way, they're going to want that faster disconnection time, you would think. But I totally understand what Craig's saying. It is it can muddy those waters and cause debate. We like a debate, don't we?
Yeah.
Sorry, mate. What screen did you want? This one?
I'll go back up again a little bit.
Back up again.
Disconnection time. Yeah. There we go. So based on it then being a 40 amp final circuit with one or more socket outlets, then it's going to have a maximum disconnection time of 0.4 seconds. So our RCBO has got to disconnect in no more than 0.4 of a second, so just under half a second. We need to guarantee it, we need to confirm, we need to make sure it will. So how do we do that? So as we go down, there we go. So in order to confirm that it's going to disconnect within the required time, we need to determine then our maximum earth fault loop impedance value, ZS, to achieve our 0.4 second disconnection time. So in order to do that, we are given a formula, and we'll find that in Appendix I of the on-site guide on page 217. To calculate ZS, we'd need to have a value for ZE, which we have from our drawing, and we'd need to add that to our resistance of our line conductor R1 and our CPC R2. So we know that our line conductor is 6 mil. We're going to use a 3-core cable, so our CPC is also going to be 6 mil. So what I need to do now, I've got to use the on-site guide for this one, or I could use guidance note 3, is to find out what my milliohms per meter value will be for our combination of 6 mil, 6 mil. So within table I1 on page 218 of the on-site guide, I need to go down and have a look for my line conductor 6 mil and my CPC of 6 mil. And I get a value then of 6.16 milliohms per meter. So for every meter of 6 mil combined, I'm going to get 6.16 milliohms of resistance per meter. Happy with that? I need to times that by a multiplier. And the multiplier value I need to get from table I3 in the on-site guide, page 220. And when we look at that table, so let me just grab my on-site guide. So let's have a bit of a look at that for you. So table I1, 6 mil, 6.16. I need to consider then table I3. And it tells us that these multipliers need to be applied to table I1 to calculate the conductor resistance to maximum operating temperature. So as soon as we turn this charger on and you've got current flowing up and down the conductors, that's going to increase resistance, and I need to allow for it. Okay? So we look at table I3, and it says conductor installation, and we've got here 2 different areas to look at. So whether it's not incorporated in the cable and not bunched, or incorporated in the cable or bunched. So is the CPC separate or is it bunched with? So conductor insulation, we've either got 70-degree thermoplastic, we've got 90-degree thermoplastic, or 90-degree thermosetting. So you can already see that a mistake has been made, which is good, because even though we can't use the current carrying capacity table because the equipment we're connecting to is not 90 degrees, the insulation of this cable we're going to be installing is 90 degrees. So the factor there is not, or shouldn't be 1.2, it should actually be 1.28. So that's going to affect slightly our value of R1, R2. Happy with that?
Yeah.
I'm going to make a slight adjustment to that, which is good, because as Dave quite rightly said, there are, you know, if you get one little bit wrong, you've got to make sure that...
just goes to show, doesn't it, Rich? That you know, we can all make a simple mistake, and sometimes it might only have a minor effect. And
I can see
you've still got your train of thought there. You still be picking up marks, even if that.
I can see why it's not there, because I haven't actually included it, because I was going to change that. I changed the 6.6 because it was something different last time, and I haven't changed the bit underneath. I think that's when we was in a Teams meeting, Dave, or whatever, and I haven't come back to it. That's why. But we can apply that now, so that's fine. So we're going to have 6.16 times our length, 26 meters, times our value from table I3, which was 1.28. I don't want the value in milliohms per meter, I want it in ohms, so I'm going to divide that by 1,000. And I'm going to then get an R1, R2 value of, and it's only gone up slightly, but it's gone up to 0.205. So we'll call it 0.21 ohms. Happy with that? So it's gone up by 0.02 of the 9. Okay. So therefore, to calculate ZS, our ZE value from the drawing was 0.14. We're going to add that to our R1, R2 of 0.21, and we're going to have a total impedance value then of 0.35 ohms. It's gone up a little bit. Happy with that?
Yeah.
Right. So what we need to do now is verify that our maximum earth fault loop impedance value that's stated in the regs for that protected device to achieve that 0.4 second disconnection time hasn't been exceeded with our calculated value. Nice and simple. So what I need to do is find the table that's going to give our maximum ZS values for type B RCBOs to 61009. So back in the regs book, I can go to page 68, and I'm looking at table 41.3. So table 41.3, page 68, and all it is just a process. So table 41.3, maximum earth fault loop for circuit breakers for a 0.4 to 5 second disconnection time, and also RCBOs. So type B circuit breakers. So I'm going to use the top row, 60898 or overcurrent characteristics of RCBOs. So I go across to 40 amps, and I've got a max ZS there of 1.09 ohms. Happy with that? So as long as our calculated value of ZS is lower than the maximum value, we're going to achieve our 0.4 second disconnection time all day long. And it's 0.35, which is miles lower than 1.09. So we're happy with that.
Again, Rich, that just comes back to what Craig was saying earlier about verifying ZS values. We've calculated the value, but what is the maximum? As long as it doesn't exceed the 1.09, we're okay. And that's what Craig was on about with verifying test results.
Yeah.
One other little tip on this particular area is always make sure you're using the right table.
Yeah.
One, for the protective device that you're using, and secondly, for whether it's 0.4 seconds or a 5-second disconnection time. With circuit breakers and RCBOs, it doesn't matter because it's 0.4 and 5 seconds in the same table. But if your question contains something with regards to fuses, BS88s, 3036s, please make sure you're using the right table for the type of fuse and the disconnection time, because it could go wrong at that particular step there, because you might be using the wrong value. So just be careful.
Well done, Dave. So next scenario then. Well volunteered, mate. You can incorporate some of the curveballs, can't you? Okay. Excuse me. So next stage then, we've calculated our max ZS. We've confirmed it against the max that's allowed, and it's well below, so we're okay with that. We then need to determine our fault current, and this is under earth fault conditions. So within the on-site guide, it gives us another formula, and it's basically a transposition of PIV, isn't it? So to calculate our fault current, we need to divide our nominal voltage UO by our maximum value calculated of ZS. So this is going to change slightly because we've got a 0.35 value. So 230 volts divided by a max ZS, which is calculated at 0.35 ohms, is going to give us a fault current there, an earth fault current of 657.14 amps. So it's more or less the same. So about 660 amps or so. Happy with that?
Rich, I was just going to ask, for people who are looking, viewing, this is the whole point of having a low ZS, isn't it? So if one's low, if your impedance is low, your fault current is high. And in fault conditions, we want to create high amount of fault current, because what it results in is a quicker operating time of the device. So it's like
and we'll see that in the next.
Sorry, Rich, I'm jumping the gun. It's just a seesaw effect, isn't it? If the impedance is low and the fault current's high, we're going to have a quick disconnection time.
Yeah, and we
It's
can
that favourite word. Sorry, Rich, is that favourite word that they talk about in exams and stuff, isn't it? About it being inversely proportional for learners that never know what that means. It's the opposite effect, but it comes up all the time just to make them sound a little bit more clever than what it actually means.
Yeah, so if you see the word inversely proportional, which is what Craig's, I can't even say it, what Craig's just said, it's basically a seesaw effect. If one's low, the other's high. So we're after a low impedance, high fault current, quick disconnection time. If it's the other way around, if the impedance is too high, the fault current's going to be too low, and the device will take longer to operate. So it could be upwards of 5 seconds, 10 seconds. So that's a real bad scenario.
And that's why they say about testing towards the end of line, isn't it? Although you should look at each point, is because that should be the point where technically your fault current should be the lowest, because it's got the most resistance in the circuit. So if you're meeting at the furthest away point, then anything closer is better. So if you're going to get shocked, you want to do it in the fuse board, not at the socket 300 meters away. Obviously, safe isolation, it doesn't
happen. So yeah, because we've got a calculated value of 0.35 ohms, not 0.33, our fault current's slightly less, just to reflect on what Dave has said there. So we've calculated what our prospective earth fault current would be. So what we can do now is confirm, based on that amount of fault current, how quickly our protected device that we've chosen, our Type B RCBO 61009, how quickly it will actually disconnect. We know we've got to disconnect under 0.4. We're pretty sure because we've compared our calculated ZS with the max that it will, but we can actually find out the actual time by using Appendix 3 of 7671. So I've got to select the right figure as opposed to a table. And if I look at figure 3A4 within the regs book on page 417, what this does is it gives us information in terms of time compared to current. So how quickly a device will disconnect based on the amount of current, etc. What I've got to do with this one is basically to make this easier for us in terms of finding out how much current is required to disconnect within a certain time. I can use the table on the right, and I've blown that up a little bit for us. So time current characteristics for our type B, circuit breakers to 60898 or 61009. This amount of current will guarantee me a disconnection time of between 0.1 to 5 seconds. So for my 40 amp device, I need at least 200 amps to disconnect that between 0.1 to 5 seconds. I've got an actual calculated earth fault current of 657 amps. So it ain't going to disconnect in 0.4. It's actually going to disconnect instantly. So I've got instantaneous disconnection. All right, happy with that? Go on, Dave.
Just to jump in, I know I'm probably doing everyone's head in. Again, you've got a value in front of you on your piece of paper at 696 or whatever it was with the adjusted value. What do you do with that? We're looking at there what we call the quick reference table. We've got a 40 amp device, we've got 200, and it's knowing, well, which way. Mine's more than that, and it's like you say, if it's above 200, it's always going to operate at 0.1 of a second. If it's below 200, we then, in some cases, it could be, especially with fuses, we might have to use the actual graph itself, and we'd have to cross-reference the prospective fault current across the bottom with the curve of the device to find out the actual disconnection time. But when we're doing cable calcs, 9 times out of 10, your fault current will always exceed the value in the quick reference table. So if your value is always more than what it says in the table, you know the T for your adiabatic equation is always 0.1 of a second. And again, it's just a common thing that I've always found in teaching and education.
I always forget the official name of these graphs.
Very useful though, very, very useful. Again, we could do a different webinar where we may not have the amount of current required, we might have less current, but again, we can use the graph to find out the exact time. And with these time current graphs, you've got a straight line and a curved line, and that relates to the technology that's in your MCB. You've got your solenoid, your magnetic part for instantaneous, and then your bimetallic strip is represented by your curved line that will operate after a certain time. So that represents your different technologies inside an MCB. So we know then we need a minimum of 200 amps. So therefore, 657 amps will achieve our maximum disconnection time of 0.4 seconds. It's going to be 0.1 actually. It's instantaneous. So again, fully compliant with shock protection in terms of compliance with Chapter 41 of the regs. Happy days. Good with that. And again, that's looked at disconnection under earth fault conditions. So maybe in a future webinar, we might need to verify that there'll be enough fault current under short circuit conditions. And those questions are quite popular within the level 4 questions qualifications. You always get a short circuit calculation. But again, that's something we can look at moving forward. But we know it will disconnect under earth fault conditions. We're well within our 0.4, so we're happy with that. Happy days. And then we're getting there. Last thing we need to do. Last thing we need to do. There's a few more bits we can look at next week because there's a few more questions in the other bit, but that's fine. We've got to now confirm or make sure that the cross-section area of the CPC that's within our cable, because we're going to use a 3-core cable, is acceptable. So we know that line and neutral are 6 mil, but the CPC is also 6 mil because it's a 3-core cable. When we look at regulation 543.1.3 in the regs, there's 2 ways of doing it. One is, one is using table 54.6, is it? Where we
So
basically
we can either calculate it or we can use a tabulated value, can't we, Rich?
but generally
the tabulated one will come out as bigger, as larger.
Yeah, using from the table. And if you calculate, it's always going to be smaller. But again, that's something we can look at. But what we do need to do is verify that what we've selected is actually larger than the minimum size. And to do that, it gives us the old adiabatic equation within regulation 543.1.3. And in order to calculate it, and this will give us the minimum cross-section area that's required, it gives us a formula to calculate the size is square root of I squared times T divided by K. So I squared is the amount of fault current that we've just calculated. We need to times that by the actual time based on that fault current and that type of conductor that it will disconnect in. We also need to find the K value. And these values you find again in chapter 54. And these are values for K for protective conductors. And it looks at the thermal properties of the copper, etc. So we've got to use the right table, and all we need to do then is put that information into the formula to do the calculation. So it's quite simple, but there's a number of tables within chapter 54. This particular table is the right table. So table 54.3. These are values for K for a protective conductor that's incorporated in a cable or bunch with cables. So our CPC is built into the cable. So we need to look down here and we need to select the insulation material. We know that the cable we're using is 90-degree thermosetting. The material of the conductors are copper. So in that case, the K value we need is 143. Happy with that? If we chose 70-degree thermoplastic, we may have chose 115, but luckily I spotted that one earlier and swapped it over because it is 90-degree thermosetting. So we put those values into the formula. So we calculated our fault current at 657.14, but we'll use what we did earlier. It's not going to affect it massively. We need to times that by our actual disconnection time we just calculated from Appendix 3 of 0.1 seconds. Divide that by 1.43, and it gives us a value of 1.5412 millimeters squared. So the minimum size CPC we need in order for it to not fall apart for that amount of time with that amount of current based on that type of conductor, copper, etc. The minimum size we'd have to put in is 1.5412. So we couldn't put 1.5 in. It wouldn't be big enough. You'd have to go to 2.5. But because we're using a 6mm, because it's a 3-core 6mm cable, 6mm is way bigger than the minimum size, 1.54. So again, cable's good to go.
Fantastic. That was a great run through again, Richard. David's got his hand up. Anything to add, David?
I didn't want to interrupt him in his flow as I've been doing, but just some more tips in that particular section. There's a few tables for values of K. So if you've got your own regs book, this is where your highlighter pen will come in handy. As Richard pointed out, we've got a protective conductor incorporated within the cable. So the armoured is 3-core. So I would suggest to highlight the key areas because sometimes it's not incorporated in the cable or it might be the armour in itself. So, you know, you've got 4 tables all staring you in the face on page 200.
Yeah.
Using a little highlighter pen will point in the right direction. The other tip is when you're doing that formula, depending on what type of calculator you've got, break it down and write it down. So where you've got S equals I squared over T, do your fault current times by itself, write that down. Yeah. Then you've got your time, write that down. Times that together, then square root it and then divide it by your K value. I've seen so many errors, people punching it all in on the calculator, pressing equals and just get a totally wrong figure. So break it, write it down.
I might square root the whole lot as opposed to just the top line. So you've got to make sure you input the information correctly on your calculator.
And it does depend. If you've got a fancy calculator, you might be able to punch it all in there. But I'm old school. I use an old, calculator with big buttons, and I can do everything on that. Breaking it down, making sure you can see where potentially you may have gone wrong. And the one thing on there where you may have missed the mark is if you just put the total, so we calculate that 1.52 millimetre squared is the minimum. If you don't put, we've used the 6 mil, so therefore complies, if you're doing a written exam, you may miss a mark there because you've calculated the total, but you haven't confirmed whether what we're using is okay. Fine. So three little tips there.
Yeah,
great point.
Again, Dave's volunteered to do us another one where we may be using a 2-core cable. So in effect, we may be thinking about using the armouring as our CPC. So then, how do we verify that, you know, the steel, because it's obviously it's got a different resistivity, and the number of strands, etc., equates to that minimum size. For instance, what we just calculated there of 1.52 whatever it is millimetre squared. How do we know that the armouring, the strands of that steel, is
adequate,
the same size? So again, Dave's offered to do one of those for us.
Perfect.
You just have a guest on you.
Yeah, basically. Yeah.
That'll be after Craig's covered the harmonics episode. That's his dedicated beast. We can't forget that. Just want to run through some of the comments that came back. So Neil Bridgman's popped in there that for apprentices watching this, bolt drop, I think David mentioned this through the recording, but just to cover it again, bolt drops the whole circuit from the DB consumer unit right the way through to the EVSE. So if the EVSE is a sub DB, so it's powered from a sub board, you need to make sure you're taking account of everything.
Yeah, it's so important. A real error again is just allowing volt drop for your final circuit and not considering anything that's sort of, you know, in front of it, sub dBs and whatever. Majority of the time you'll be given a value, so it'll say the distribution circuit volt drop is 1.5 volts, and obviously it's very simple. You just add that to your volt drop and then compare it with the maximum. So it's like an accumulative volt drop, so it's from the origin all the way through to the end of your final circuit. You're not allowed 5% for your final circuit. Imagine if I've put a dB in my shed in the garden, and then I allow 5% for lighting from there for garden lighting. I haven't considered the sub main. So a great comment to whoever's put that in the chat. Well done for spotting that one. Yeah. But
again, we can create another example. You know, taking a circuit from a sub dB where you might already have a volt drop at that point of, I don't know, 6.4 volts. You've got that to start with already. So then you haven't got 0.5 anymore, have you? Or even less lighting, etc. Yeah.
I mean, I used to be involved with a lot of design, and we used to allow, you know, around 1 to 1.5% on distribution circuits, because otherwise, if we allowed any more than that, and we've only got sort of 3% for lighting, if I allow 3% on a distribution circuit, your lighting circuits are 0 meters long. So you know you've got to be sensible with things like that. It is from the origin all the way to the end, not just your particular section. So
I was just going to add to that I couldn't possibly say where it maybe happened, but those that are looking at doing other courses, one of the recent questions was actually working back the other way. So it gave you the lengths of your final circuits, and you had to then work out what the allowable voltage drop was for your sub-main. So maybe we'll look at scenarios going that way as well, when you're taking into the fact that you've got a lighting and power board, and the difference between 11.5 volts and 6.9 volts, what's giving you your worst case scenario to actually work out your sizing of sub-main, because I think that's something that's missed going back the other way when people are looking at what boards are fitting.
It's a good point. There's been a few questions in the Q&A that Craig's kept on top of us for, so cheers for doing that, Craig. But it's around the BS numbers for EV Ultra. I'll have to check that, to be fair. I think it's in there.
Departure.
Yeah. So that was the departure. That was Kevin Smith who said, is it a departure or is it actually listed in the regs?
Yeah, it is a departure. So the cable has been BASIC approved, but it doesn't have an actual BSEN number because of the fact it's mixing power and data. So the cable should be a departure on your certificates when using.
That'll be the same for the PV Ultra as well that I've seen shared, I would imagine. So one to bear in mind when you're looking for something to put in that box. We all want something to go in there. So that's something you can chuck in.
Well, yeah, I mean, I've included that in question 10.
Yeah, I was just having a quick scan through that. So anyone who is still watching, and obviously I'll be sharing this on YouTube afterwards anyway, Richard's popped some other little things that could crop up as some extra questions on top of the scenario, and he's covered that in there.
In table 4A3, obviously, it's schedules of cable specifications and current ratings of tables that are recognised by the standard. And of course, it doesn't have a standard, so therefore it would be a departure. But as we know, as it says in 133.5, where the use of a new material or invention leads to departures from the regulations, the resultant degree of safety of the installation should not be less than obtained by compliance with. Such use shall be recorded on the appropriate electrical certification specified in Part 6. So, because it's not recognised, you'd have to list it as a departure, but you should really include or append all that manufacturer's technical documentation should be appended to it. So then, if anybody's doing an EICR, they might look at it and say, "Well, I've never seen this cable before. That's dangerous, that is, because you've got ELV with LV, and you can't use that. That's dodgy, etc., etc." So,
I think Neil's. Sorry, Craig.
Sorry, I was going to say Neil's put a nice one in for you to finish with on whether open is then also a departure, and whether the built-in RCD with no test button would have to be a departure on the set as well.
Well, if you go up a bit, Mark, you'll see that there is a bit of information on that because we've had a bit of it. So you've got to consider, and we've covered the RCD part, but you've got to verify from the manufacturer's technical guidance or the documentation that compliance with 712.411.4.1, including note 1, has been complied with. So we know that we've got 4 options now within 722.411.4.1. Option 1 is where we put an additional earth electrode to supplement the PME, but the value of RA has to be so low you'd never achieve it. Then it gave us these 3 unicorn devices, didn't it? Indent 3 was Matty's type of technology. Indent 4 is what most single-phase chargers use. So Indent 3 is, in effect, measuring voltage between the protective earth of the circuit and true earth. Or you can do it where you derive a reference point from the 3 phases and measure the voltages. That's what Matty's does. Or option 5 is some technology that's not listed, but is equally no less safe than 3 and 4. And when you look in the manufacturer's data for this charger, it actually lists compliance with Indent 5. Now, we don't know if that's going to bloody work. It's not in this one. It's in another one on the website, I think. Yeah, it just says there, but it's actually listed in another document. When you go on the website, I didn't give everything to them. If you follow the link, it tells you where to find it. But in note 1 to that 722, the 411.4.1, it actually says that and this is what got changed in Amendment 2, which is quite nice because we can't say whether or not that this device is going to work, can we? We don't have an open tester.
No, I think that's what kind of Neil's alluding to there, that it's a wiring standard in terms of BS 7671, and this is more a product standard if the pen fault is within the EVSE charge point. And I guess that's kind of what the regs are saying with the notes on that indent.
Section 511 doesn't deal with the safety requirements for construction of electrical equipment. So what we must do is we must obtain from the manufacturer, and this is difficult, or can be, we need to obtain the declaration of conformity to verify that they take responsibility for that technology. And actually, the declaration of conformity is on the website. You can download it for free. Mint.
And
I would put myself out there with Neil's question, and happy to be wrong, but I would say if you're installing a Matty or pen type device, and at the minute I would class that as a departure. Yes, it may need to be there. It may be something inside the charger, but I would probably note it as a departure on my certificate to say that it's not necessarily something with a BS number, as far as I'm aware, but I haven't looked at them for a long time.
And I'll add to that with the built-in RCD, if you're relying on that in the EVSE without anything up front, then that would be a departure as well. And that's why we always fit the RCDs up front of these things, because most of them all have the electronic devices. But I appreciate we're running on a bit long now, and you probably all need a toilet break and a drink, so I don't want to drag this on any longer. I think we can come back. We can come back and take a lot more from this later on.
I mean, I only got so far with it, but there's a few other considerations. The fact that the RCD or the RCBO needs to be double pole, and most of them aren't. So again, I'll add a bit of information on how to find that. There's a bit of a cut there that I took out of the Beamer document on RCDs, really useful, the one about different types of RCDs and where you can and where you can't have them. Because again, no information was provided with the question as to what is upstream, because we might have an existing DB that's got type AC RCDs in it. You can't have a type A, an F or a B downstream of a type AC. So in reality, we'd end up replacing them or doing, whatever. So that, quite a few considerations there that we can.
There's loads of stuff. We can go down some rabbit holes and a half with all of this, and there's lots of other subtopics to come up to. I just want to thank you guys for giving me your time to come and chat with me. I've loved sitting here watching you all talk, trying to keep on top of the buttons and the recording and stuff. Otherwise, I've contributed very little to this evening's proceedings. So thank you. And those PDFs that Richard's produced will be shared on the Apprentice One-to-One website. Yeah. It'll all be on there, the answer sheets and all the links where you can go off and find other bits and pieces. For everyone who's joined in with us tonight as well, I really do appreciate it. The apprentices who are maybe going to watch this later will get great value from your input as well. And just to say, this isn't paid or anything, but if you want to go and download Electrical OM, you get a 14-day free trial. And if you're going through this design process by hand, it's sometimes useful to check it off with the software. It gets you used to it because it's what everyone's using out in industry or something similar to that. And you can see where your correction factors, rather than diving into all the books, you can make simple changes and it adjusts it all for you. So for lazy people like me, who this afternoon wanted to get the answer to Richard's questions, you can do that and cheat the system. No, it's just a good way of verifying your own work. But thank you, gents. Is there anything else you'd like to add before we finish? Sorry, Craig, you had your hand up there.
I was just going to say, following your comment, this will be my final comment, is for those that are in colleges and are apprentices listening or watching this, I know that the guys over at Electrical do training for colleges and do educational licenses as well. So that is, pick on your tutors. There is a way for them to come and do support and show you this and give you an insight into what people are using every day whilst you are still learning. So the first time you come up against something like this isn't when you're out in industry, and it is free or very cheap, I believe, for the educational stuff to be put into your college. So go and speak to them and you'll get some good information out of them.
Top stuff. Anything else anyone else would like to add, or should we end it there, gents?
No, just from me, just hopefully it's been some help. Been a pleasure once again, Craig and yourself, Mark. Nice to have my compadre with me. I know that, if it helps anyone, that's the whole reason why I try and get involved and try and help the same as you guys. And I know that Dave, hopefully he's enjoyed it and inputted a little bit.
Yeah.
And he's going to come up with a scenario.
I was going to say, I've enjoyed it. I hope I've been a help rather than a hindrance, and I've kept butting in. But it was just to bring some of it to people's attention and common mistakes what people make. So, but yeah, I've enjoyed it. Thanks for having me on. Nice to meet everyone.
No, cheers for coming on, David. I really appreciate your time. Thank you again, Craig. Thank you, Richard. And this will all be shared out through the course of the next week as well. So keep an eye on the social media handles. We'll see you on the next one.
Awesome. Take care, guys. Later.